In the last video, we introduced graphs. So now we're going to go ahead and explore how to navigate through a graph using the two techniques of traversal, that is breadth first search, which refer to as BFS, and depth first search, which in short we refer to as DFS. So this graph traversal helps us explore every node and edge basically in a graph, which is useful for applications. So applications in things such as finding the shortest path. We're checking for cycles or looking for to explore connected components. So graph traversal helps us in such situations. So now I'm going to go ahead and start with the breadth first search, and let me just write it here. So I'm going to start with BFS. And BFS, what we refer to as breadth first search, is a graph traversal technique that basically uh, it explores the graph level by level. So if you have a graph, so this is have some text here. So let's just say it explores graph level by level. Level by So it explores a graph level by level, and basically how it does that is it starts from a given vertex, then it visits all the neighbors in that vertex. So if you have an example of a graph like this one here, it's going to start with let's say we start by visiting starting from 12. So if we start from this node here, then we're going to visit basically the neighbors of this 12, then move to the neighbors of those neighbors. So the neighbors of 12 here are 4 and 5. So we're going to visit 4 and 5, and then go deeper into visiting their neighbors as well. So that is how basically BFS works. Now, another thing to note about BFS and how it works in sort of in detail. When we are working with BFS, we use a queue data structure, and we use a queue data structure with the FIFO pattern, the FIFO principle. And this here is an example of a queue. It's an example of a queue that we can use. So we use a queue such as this one, just for sort of a reminder. This is how a queue works. So there's the front part and there's the rear part. The front part is the one that gets served first and is following the FIFO pattern, and the rear part is the last one to be served. So you use a queue data structure in BFS, and like you mentioned, it starts from a given node, and then it explores all the adjacent vertices first in a breadth first manner. And once all the neighbors are visited, it moves. So if you start with zero is the node that it starts with, it visits all the neighbors. And once all the neighbors are visited, it basically goes and visits the neighbors of those neighbors. So just to have some sort of precision in terms of how this BFS algorithm works. So we first start with this. So in a BFS algorithm, we first of all start by initializing an empty queue, and then we add a vertex to it. So initialize, we initialize an empty queue, then we go ahead and add the starting vertex. So add starting vertex or node to it. So after doing this, the second step in our BFS is going to be now marking the starting vertex as visited. So just mark starting vertex, or let's just go with node for uniformity here. Starting node as visited. And once we've marked it as visited, so now that allows us to go and start looking at its neighbors. So the next thing that we're going to check if the queue is not empty. So if you find that the queue is not empty, so you can just use while here. So we can just say while queue is not empty, While the queue is not empty, then here now we start exploring other things. So the first thing that we do while the queue is not empty, the first thing we do is we're going to dequeue the front element from the queue. So again, in a queue data structure, we removing the front element is dequeuing. That is now serving the first element. So we're going to dequeue the front vertex. So we dequeue the front vertex or the front node here. And after dequeuing the front node, then we start looking at each of the adjacent nodes to that node that we dequeued. So we look at the adjacent nodes. Just say so basically look at adjacent nodes. So adjacent nodes, here we mean adjacent nodes to the dequeued node that we've already looked at. So once you've looked at the adjacent nodes to the dequeued node, what we start doing with this is we check if they have already been visited. So check if visited, so we check if the adjacent nodes have been visited. That's the adjacent node to the dequeued node, that is. And if it hasn't been visited, so we can just say here, if not visited, we go ahead and mark as visited. It has not been visited, we go ahead and mark it as visited. Then after marking it as visited, we basically add it to the queue. Now, the process of adding an element to a queue, that is what we refer to as enqueue. So basically, if it's not visited, we mark it as visited, then we enqueue it. Basically, again, remember we had started by initializing an empty queue at the beginning, where we were adding the starting node. Then we mark it as visited. Then we go to the neighbors of that node, and we check if that neighbor has been visited. If that neighbor hasn't been visited, we also mark it as basically we sort of like add it to the queue. Then we mark it as visited, and that process is going to continue like that. So an example of a breadth first search traversal, we can just try to demonstrate a similar thing here. So how that would look like. So let's say we have an element A, then we have an element B here. Again, this we refer to them as nodes. I just keep on referring to them as elements. Then we maybe have we have a C here. Just have C here. And then from C, here after the B, we have maybe we have a D here. Not a D, but an E. So let's say we have another node called E here. Now, if this is a simple graph that we're trying to do some BFS on it, what we'll do is we're going to start with the starting vertex. And if we start with a vertex like A, so we're going to start with the A, then we are going to enqueue A. Basically, we enqueue A and then we visit its neighbors. So again, that means we're going to have a queue. So if we have a queue, rather the first process that we said, we initialize an empty queue. Then after, now this A is the first we're starting with, and then we enqueue this. So by adding it to the queue, then we go ahead and visit its neighbor. So the neighbors of A are C here and B. C and B are the neighbors of A. Then after doing that, we're going to basically dequeue A, then we're going to enqueue B and C. Right? So we dequeue A. Again, as you can see, this is the next step that we went here. We dequeue A, that is now the front node. Then we go ahead and enqueue B and C. Then after doing that, we're going to visit the neighbors. So in this case, B is the one that has neighbors. So we visited the neighbors of B, which will result to us in queuing E and D, which are the neighbors of B. Then we continue until all the nodes are visited. So we basically repeat that process until all the other nodes are visited. And that's basically what BFS is, or how BFS works. Now we're going to go ahead and look at another the other graph traversal algorithm or method, which is DFS. And DFS is depth first search. So looking at DFS here, the way DFS works is that, again, it's also a traversal algorithm, but now this one explores as far as possible along a branch before it does the backtracking. This one goes to basically every other node that is attached to the starting node, or the current node that it's working on. But in DFS, it goes a bit deeper from that node, and we're going to see how that works. So unlike the BFS, this one dives deep into the graph. Then it follows a path from the starting vertex. So if this was a starting vertex, it follows down to the leaf. So it follows down to the leaf before that it does its backtracking. And we'll just quickly start with how DFS works. So how DFS works generally is, it uses the way in BFS we're using a queue. In DFS we use basically a stack data structure. So we use a stack data structure which follows the LIFO principle. And it can be the other thing that you can do, we can use a stack, or we can basically implement it recursively. So use a stack or recursion. Let's see, stack or recursion. So these are the two methods that you can use to basically implement your DFS. And of course, in recursion, you're using function calls in this case, and we're going to look at both of them. Then basically DFS starts from a given node. So you define the given node just like in BFS. Then we're going to, the difference now comes in terms of how deep we explore, basically before doing the backtracking. So just to look at the algorithm, the DFS algorithm and how it works. Let's do this in white this time. So how this is going to work, how the DFS algorithm works is, first you start by initializing an empty stack. So we're going to start with the iterative approach. So we're going to just call this DFS iterative approach. Iterative approach. So the way the iterative approach works is, we first start by initializing an empty stack. So initialize an empty stack. Then after initializing an empty stack, we push the starting vertex or the starting node onto it. So initialize empty stack and push starting. Let's use vertex this time instead of node. And we push the starting vertex into that. Then after doing that, the next step that we do, just like before, is you mark the starting vertex as visited. Mark starting vertex as visited. So after marking the starting vertex as visited, now we try and check if the stack is empty. And while the stack is now empty, that is assuming it's empty, while the stack is empty, what you do while a stack is empty, the first thing that we're going to try and do is, we're going to pop the top vertex off the stack, from the stack. So we're going to pop the top vertex from the stack. Again, we've looked at the stack data structure before, and we know these methods that we follow, so like pop and all. Then after popping the top vertex from the stack, the next thing we do is, we're going to check for the adjacent vertices, basically. And for each adjacent vertex, that is now the adjacent vertex of the popped vertex, we do a few things. So just say here, for neighbors, just say for neighbors. And by neighbors here, we mean the neighbors of the popped vertex. So for each of their neighbors, basically what we do is, we check if the neighbors haven't been visited, or if they have been visited. So we're going to check if you've not visited. Say, let's assume they have not been visited. If the neighbors are not visited, the first thing that we're going to do is we're going to mark the neighbors visited. So we're going to mark as visited. Then after marking the neighbors visited, we basically push it to the stack. So we'll just push it into the stack. And that is basically how DFS works. As you can see, there's some key differences between the two, and that is how deep it's gonna go to check for whether to check for the visited nodes and all. Now this is the iterative approach that we've seen here. So I just mark with this is the iterative approach. Now the recursive approach, which is the other approach that we can use, we just call this here recursive approach. Is, huh, recursive approach. How the recursive approach looks like now here is we first of all just start at a given vertex, which is a given. So start at a given vertex. Then after starting at a given vertex, the next thing you do is just mark it as visited. So we mark it as visited, should be a V here. We mark the starting vertex as visited. And then the next step from there is going to be now recursively visit each of the unvisited neighbors. So here this is a recursion taxon. So we're going to recursively visit each of the unvisited neighbors. Each unvisited should be an S here. Each unvisited neighbor. Yeah, so that is how the recursive approach is going to look like. So if you use this example here, just use this example to demonstrate this. Let's have it here. So if you use this to demonstrate how the DFS traversal works, is we're going to start with let me use white. So here we're going to start with the vertex A. So we declare A as the one that we're going to start with. Then after visiting A, remember we go as deep as we can until we reach the leaf nodes when we talk of the depth first search. So and then we're going to go ahead and look at B, then finally go look at D. Then after we've reached D, we backtrack to B. Then from B, we go ahead and visit E. And again, we can go as deep as possible. So if E has multiple other nodes or vertices to look at, we're going to go and look at all of them. Then after we're done with that, we're going to backtrack. And then now we backtrack back to A. Then we go and look at the node, the neighbor of A that we hadn't visited, which in this case is C. Go ahead and look at that. And we can go as deep as possible on this one. And this is basically how you do the depth first search and the breadth first search graph traversals. These are the algorithm or the sort of step-by-step processes that we follow when you're using the both traversal algorithms. The difference between the two, as you've seen, is that in BFS, we explore all the neighbors at the present before moving to the next level. So if you are starting with A, we see all their neighbors first before moving to the next node or the next vertex. But in DFS, you explore a specific node as far as possible, a specific route. So you're starting with A, you go as deep as you can and then after you're done with that, you backtrack and start visiting the others. And the other major difference is in terms of the data structures that we use. In BFS, we use a queue to look at it, and then in DFS, here as we've seen, we use two things. We can use a stack, or we can use recursion, where we use some function calls to implement that. And in terms of applications of both of them, the BFS is good for basically finding the shortest path in an unweighted graph. So we looked at graphs yesterday we saw both weighted and unweighted graphs. And so we can use BFS to find the shortest path, and any other sort of level order traversals, even in trees, we can use this. But when you talk of DFS can use it to solve mazes. If you're checking for basically some cycles somewhere or detecting them, you can use DFS. In this case, a method like recursion would work really well in that. But even a stack as well, when you're dealing with recursion, you can still use it to work efficiently. Now, in terms of the term complexities, the term complexity of both of these algorithms, that is DFS and BFS, they both have let's use a blue here. Yeah, so the both BFS and DFS, they have a term complexity of O of is it they have O of V plus E, of V plus E. That is their term complexity. And what you mean by the both of this is that V stands for vertex, and then E stands for the vertex or the vertices, that is. Then E stands for the edges. So you can just say here vertices. Then this other one here it stands for the edges. And that is basically it about BFS and DFS. We've looked at how they work, basically the best methods and data structures for them, in the term complexity for both of these, which is O of V plus E. And that is it. Thank you for watching this far. I'll see you in the next one. Cheers.